Back. We are on lecture 2 of our polymer course, and today, or this time, we're going to get into, you can see there's lots of kind of key terms and definitions here. Today we're going to be talking about molar mass, in this video in particular, molar mass, basically number average molecular weight versus weight average molecular weight, polydispersity index, then, so that'll be our kind of first video, we'll talk about basically the Carruthers equation and the extent of reaction P versus the reactant ratio R. Then we'll talk, in another video, we're going to talk about step versus chain growth polymerization, and related to that is condensation versus addition reactions. We'll go a little bit into the kind of the reaction to the kinetics, reaction kinetics equation, so hopefully you remember that, specifically this guy goes to CC plus DE, what is our K equilibrium, and basically how that affects polymerization. And we're going to talk about lots of different types of basically step and chain growth polymerization processes, and different classes of chain growth in particular. So it's a pretty dense lecture. Also, it is kind of chemistry. Remember, we are not chemists. We just need a little bit of chemistry to be just dangerous enough as basically polymer scientists, polymer engineers. So don't be too overwhelmed by it. We'll take it a step at a time. So today, in this video, we're going to focus on these guys. That'll be enough. Molar mass, and some of these other kind of key critical parameters that we need to kind of characterize as polymer scientists, because again, we saw last time how structure affects properties. These kind of quantities will also affect basically the properties of your polymer. So just a reminder, polymers composed of monomers or different structural units, whichever you prefer. Again, you'll see different types of literature will refer to it differently. So 100 times if n, or if you have that number of structural units or repeat units or monomers, 100 repeat units, that's typical for oligomers. 10 to 100K is typical for your macromolecules or polymers. So last time we said that n was the number of times we repeat this repeat unit. I'm not trying to repeat myself. Fun. That's really nice in my lecture notes. Anyways, but now we are going to talk about one of the key parameters that we didn't discuss, was molecular weight or your molar mass distribution. So you'll see this kind of said interchangeably, molecular weight, molar mass. Molar mass, or actually your molecular weight or molar mass distribution. So we're going to typically, molar mass is actually the more, I think, correct, or the term that I like better, essentially, but you'll see molecular weight, and actually we'll use the term molecular weight quite a bit in literature as well. So the key point is just that the molecular weight of your polymer, or the molar mass of your polymer, will actually have a big impact on the viscosity of your material, usually ultimate tensile strength as well. So the molar mass is really critical to determine, remember, properties. That's what we're focused on. So you can imagine, right? And we talked about that a little bit last time. The longer your polymer chain here, the more, as that scales, as n increases, we increase our number of intermolecular interactions, potentially. So that increases, and that will increase if your polymer is thermoplastic and it's crystalline, your melting temperature will increase, stiffness may increase as well, if packing is efficient. The strength of those interactions, force, remember, force of your van der Waals, it decays as d-6. So as we kind of pack those guys closer together, all those properties change. So that's what we're working with and kind of trying to figure out here. So how do we calculate molecular mass, molecular weight? Well, if we're dealing with a single homopolymer, and we're going to talk more about copolymers and blockopolymers in a bit, but let's just think of an example for simple homopolymer, just like polyethylene right here, which is formed via chain growth. More on that later. Sometimes called an addition reaction. Chemistry is coming, beware. But dang, don't worry, it's just chemistry. It's easy, at least for us. So if we want to calculate the molar mass, or the molecular weight of our polymer, it's just going to be defined simply here. So our molar mass is just going to be the number of times our monomer unit or repeat unit is repeated, n, times the molar mass of the repeat unit. So if we look at basically polyethylene right here, for example, I'll just redraw it. I always draw this guy. So here's our repeat unit, repeated n number of times. We just plug in that value right in that equation here. What's the molar mass of this repeat unit? Well, we have 2 carbons, so that's going to be 4 grams per mole. So again, you can find those values. We have 4 H's, those count as 4. So our molecular weight, our molar mass is going to be 28 grams. That's it. That's all that we're kind of dealing with here. So pretty straightforward. Multiply that, and you could find out the molar mass of your polymer. So why aren't we done with this lecture? Well, this would be perfect if this was again, chemistry was easy. We would never have to kind of talk about essentially the molecular weight distributions, which we mentioned up here previously. So there will typically be, and that's why this number is kind of a little bit misleading. But in real life, when you're synthesizing a polymer, it's a chemical reaction, right? As we kind of noted a little bit up here, this K equilibrium. Oops. We introduced this K equilibrium constant, so reactions are never going to occur, exactly the same everywhere. There's temperature fluctuations, things happen. That's why chemistry is complicated. It's not easy. So when we synthesize polymers, not all of the polymers are going to be the exact same length. So we're going to get N changing. So it's not going to be really, it's never just one number like 100. Instead, we're going to get some polymer chains that are longer, some polymer chains that might be a little bit shorter. Again, they're not going to vary by a lot as long as you do the chemistry properly and there's no side reactions, but there's going to be some, again, hopefully you've seen this before. I'm looking at molecular mass. There's going to be some distribution of molecular weights. So we need to calculate those. We need to figure out what are those average quantities. And so we are going to be concerned with today about the number average molecular weight and the weight average molecular weight or molar mass. So the number averaged is just going to take into account some of the products of the molar mass and the fraction of these moles. So the number average is going to say, okay, if I have, I have polymer chains, like this is my distribution. I have some big polymer chains, 3 polymer chains, 2, 3 of different length. I want to see how many of basically the lengths of this kind of one category do I have versus 2, 3, and 4. Again, we'll see this in an example. But if you have mole fractions, the equation is relatively straightforward here. But usually you'll be given, or actually you get a readout of basically the molar mass and the number of the change and the number of that molar mass, the number of chains, and then the mass of each of those chains. So again, in my little core schematic, so you'll have like a bin, let's say one of our, let's see, we have 100K grams per mole, and we have 10 of those chains. And then you might have 90K per mole, and you might have 50 of those chains. And then again, 80, et cetera. You see where we're going here. So to calculate the number average molecular mass, you would use, if you have this data set, if you have these values, and again, we're going to talk about how do you get these values to begin with. That's a big question. I mean, if we have all those values, it's relatively simple, but as polymer scientists, we're going to look at different techniques that we're going to use to actually measure and figure out how do we measure, or how do we know how many chains are this particular molecular weight. So there's really cool characterization and techniques that we're going to introduce a little bit later on. So number average molecular mass, molecular weight is just going to be, again, the sum of the number of the polymers with a specific molar mass m sub I divided by the total number of your chains. So hopefully that's a little bit straightforward. Weight average is very, very similar. It's very, very similar, except again, it's this weighted average. So the weight of the polymer chain matters here. So you could see here that the weighted average just takes the number of a specific, number of those polymer chains n sub I of a specific molecular mass m sub I, and we're going to divide that by the total mass. So you could rewrite, with this definition, you could rewrite this equation like so. Now, one of the unique things you'll notice here is that the weighted average, and we'll see that in a problem right now, is always going to be larger than the number average molecular weight. This is the case because larger polymers are going to weigh more, so it's always going to skew to the right. Actually, we have a nice little, let's see if I can get to it. When you look at the distribution of basically a molar mass distribution curve, so the weighted average, you'll always see kind of this kind of shape. So m sub w is always to the right of m sub n. So that's kind of the key thing. You'll always see this. This is always going to be reproduced. It'll always be greater than or equal to m sub w. greater than or equal to, let's see, and just it's always going to be greater than or equal to. Usually you never really get back to equal to, but we'll see that in a second. So that is how you calculate the molecular weight average. And then with those two values, then we could kind of quantify basically what is, we kind of comment on the distribution of our polymers. So we do that by calculating the Polydispersity index, or the PDI. So it's a measure of the basically the breadth, how wide is that distribution here. So that basically this can never be less than 1. So the perfect, if we have perfectly, if we made polymer chains of exactly the same length, your PDI is equal to 1. That really almost never happens. Really, realistically for polymers, it can vary this value between 1.05 and 50. Most polymers will be between 1.2, 1.5, and 2. We can never, we can never be less than 1. That's kind of critical, and again, that falls from this definition of molecular weight averaged over weight average molecular weight and number average molecular weight. Excuse me. So that's what we're working with moving forward. So let's kind of put this into an example and work through this together. So I want you all to calculate the M sub n, M sub w, and PDI. So those three properties here for a polymer sample created by mixing 1 mole of a 50-gram polymer with this polymer as well. So let's get to it. How many number of polymers do we have? Well, we have 1 mole, or 6.0. Again, you could calculate the number of particles. 1 mole of this molecular weight. So 1 mole of 50 kg per mole. And 1 mole of 150 kg per mole. So that is our distribution. If we look at our probability, molecular weight, we have equally, if you look at those, if you created a Gaussian, it'd be 50, 50, 150. Okay, gram per mole. So let's just calculate the M sub n, MW, and PDI. So we're going to open up our Mathematica notebook. So my polymer 1, it's going to be this. I'm going to flip my screen. So I have a polymer sample here. Those are my two basically weights. So N sub n, just as we discussed previously here. Let's go back to our definition. M sub n is just going to be the sum of Ni, so we have number of chains, equally, or X sub I, your mole fraction. So right here, your mole fraction times this is just going to be the sum of those. So let's go to right here. We'll calculate this out. So we have the number of chains times the mass divided by 2. That's it. So here's your N sub n. So let's go back here. Actually, let's pull up and see if we can look at this guy simultaneously. Yep. So that's your number of chains. So 1 chain that is, or 1 mole of chains, again, it's just equal, it's effectively the same. Or 1 mole of this chain versus 1 mole of this chain, and you're good. So you divide it by 2 moles in all. That's the number of chains you have in your system. So you're summing those. So again, the 1's included here. So that is your number average molecular mass. Now let's do the weight. Same thing, except we have to square it. So M sub W is just the square of the number of polymers of chain 1. So 1 chain, or 1 mole of this, first molecular weight, or molar mass, repeat unit, or exactly molar mass, P sub 1 squared over, again, just your sum. So it's just P1, P2, the number of chains times that, plus this. And you'll see, again, sanity check, this molecular weight is greater than here, 100K. So we want to calculate the PDI. That's just going to be right here. So that's it. 1.25 looks like a pretty normal polymer to me. Actually, looks pretty good. Again, a little bit lower. The closer we are to 1, if we had just 2 chains of polymers, or 2 moles that were both, for example, 150, 50K. Let's see what's going to be. So let's make these equal. Actually, our PDI will just be 1, as you might anticipate. But because there is some, never really hit that, there's always going to be some distribution. You see that PDI grows. The larger that difference, so if we have 10,000, again, it's kind of related to that width, that distribution. We have 10,000. you see PDI is going to grow. It's 1,000. And again, you can see as that Gaussian changes or it becomes wider, this is going to grow, grow, and grow, and grow, and grow. So that's kind of that's the first problem. So there we go. That's all that you have to kind of work with and deal with there. So let's go back and do a couple more definitions here. So we have talked about one of the parameters that we haven't discussed so far is this kind of degree of polymerization and the number averaged degree of polymerization. So like we just said, in your polymer chain, not all of your polymers they don't have the same molecular weight. They're not going to have the same N. So we're going to define, again, some type of average or distribution of weight averaged and number averaged degree of polymerization. And you can see here, once you have your N sub N, all it is to get your degree of polymerization, you just divide out by the mass of that repeat unit. So again, for here, it'd be that 28 grams per mole. So that's all that we're kind of dealing with here. Now, you'll see in the, so this is the number average, that's what that N is for, weight average. You'll see that in these expressions, they're also a function of something called P, which is essentially the extent of the reaction or conversion. So it tells you how long, basically, the extent of the chemical reaction. This is going to depend on a lot of different factors. We're going to talk a lot about that in kind of your chemistry or, the polymer chemistry section. So it depends on pH, obviously, temperature, time is a critical one, side reactions, kind of the reactant ratio, kind of how pure your kind of monomer units are. There's a lot of different things that kind of go into this section of this course. So don't be worried too much about this. So we will, let's actually do one last, now that we have this definition, let's do one more quick problem, and then we will call it a day. So there's going to be more problems on these kind of degree, number average and weight average, degree of polymerization, molecular mass. So again, just focus on, there's going to be some number of polymer chains, some number of mole fraction, or some distribution of the weights or molecular mass. So just deal with those, and we're going to do a couple more example problems I'll post a little later and in the class as well. Let's do one more problem. So I have a sample of polyethylene oxide. So PEO is a really unique polymer. It is basically simultaneously hydrophilic and hydrophobic. It's a stealth polymer. They use it a lot for basically a lot of bio applications where you don't want kind of reactivity. You kind of cloak this polymer. So it's not attacked in biology. But anyways, in coating surfaces, there's a really ubiquitous polymer chain. So this is our polymer. So we already know, okay, this is my repeat unit, some N times. So I know I have 2 C's. So my carbon component would be 4 plus 1 oxygen, that would be 16, plus 4 of them, 4. Do some math. Your molecular mass of your repeat, it should be 44 per mole. So we've already identified, once you just see the polymer, just calculate those values out. So now we have, so you have a sample of PEO where all the chains have number average degrees of polymerization of 10,000. So that was, we had this perfect sample initially, but we chemically degraded it, or it got chemically degraded. Who knows what happened? That's where chemistry kind of comes into play, into equal molar amounts of chains with a DPN of 7,000, 2,000, and 5,000. So we basically, you could think of it as like 3 different, basically moles, equal molar amounts. So 1 mole that has DPN of 7,000, then 2,000, and 500. So we need to calculate M sub N, N sub W, and PDI from this polymer sample before and after degradation. So let's go ahead and get to it. So we know, let's go back to, let's see if we could pull up Mathematica, or OneNote on one side, Mathematica on the other side. So before, that's just my repeat unit. Mathematica. So previously, I have my repeat unit, so I know X, and then I could solve basically for my molecular mass. So we would need to solve for all these values before and after. So before degradation, my DPN, so let me type this out. So before degradation, my DPN was 10,000. So no other mass fractions, so I know PDI was equal to 1. So I've solved that. PDI is done. Now I just need my N sub N and N sub W. If my PDI is 1, and we know kind of our equations, I'm back here, one page, that dPn is 10,000. I know my MR, my molecular mass. I'm just going to change this to the PEO subunit structural unit. So this is essentially your sub R. So if I want to figure out what is my X, which in this equation is my M sub N, so my number average molecular mass is just going to be 44,000 grams per mole. What about M sub W? The exact same thing, right? Why? Because we know that PDI, from the previous section, PDI is M sub W over M sub N. If PDI is 1, then M sub W must be 1. So that first question was pretty straightforward, hopefully. Again, go back through that slowly and convince yourself. Now, afterwards, I have equal amounts, molar amounts, of dPNs of 7,000, 2,000, and 5,000. So now we need to figure out what's the M sub N, N sub W, and PDI of our polymer sample. So let's go about and see how we could calculate that. So first, let's figure out what is basically the molar mass of my polymer chain. So I know that dPn, so let's go back again to our definition. dPn is just M sub R. So if I want to figure out the number average molar mass, that is just going to be dPn times our M sub R. So we're going to do that for each of our polymer samples, here, here, and here. So we could do for that P1 sample, M sub N is this, my P3 is this, and my molar mass P2 is this. So that's the molar mass of each of those molar amounts. But my number average molar mass has to be what? Well, I need to add all those. They're equal molar amounts. Add them all together, divide by 3. That's your N sub N. And to do molar number average molecular weight, similar procedure, right? So again, just like we saw last time, equal molar amounts. So we're lucky. So it's just going to be what's the number of moles or number of polymer chains? 1. So that multiplied by this or squared, then divided out by, again, the sum of those number of moles or number of chains times that molar mass. So if that, sanity check again, N sub W is greater than N sub N, and we find out PDI a little bit greater, but again, within our polymer range. So that was fairly quick. I'll probably be posting an example of basically how you'd solve this problem, but that's essentially how you work with these definitions. So key things to remember, again, we don't really have a perfect scenario or a perfect situation where our sample is going to be completely basically homogeneous and polymers are going to have the exact same end. No, there's chemical reactions. We're going to have some distribution of our molar masses here. And that distribution, we should always try to remember, is going to have a molecular weight averaged, weight average molecular mass that's greater than N sub N. We can kind of quantify the probability or the distribution of those molecular weights by this PDI measure, polydispersity index. Again, that's always greater than or equal to 1, usually between 1 and 2 for polymer samples. But again, it could vary between 1.05 to 50 potentially. 50 is a very dispersed molecular mass. And again, why do we care about these polydispersity indexes? Well, if your application requires a specific stiffness or melting temperature, if you have this kind of wide, super large range of molecular masses, who knows what sample can melt earlier or what's going to kind of happen to your polymer sample. So for specific applications, we need a really, really tight distribution in order for our properties, again, to behave as we might anticipate. And they can be deadly. So next time, we're going to generally talk about thin growth, step growth polymerization, and we will get into the difference between those two. How can we kind of identify what are the key steps? And then eventually we're going to get into some Carruthers equations, and then finally into some chemistry. So that's about it. Keep an eye on the lookout for that kind of another example of that molecular weight, a little bit more difficult one. But again, very similar procedure. Shouldn't be too, hopefully, ambiguous. But I will talk to you next time. All right. I'll see you all in a bit. Let me know if you have any questions, and have a great day. Thanks. Bye.